Hi everyone, I want to take you through my solution to problem 18.2. So we're asked to express the surface integral as a volume integral. So for part A, we got this, we got a normal vector, we got a stress tensor, and we got a velocity, or excuse me, a stress vector and a velocity vector. So we go ahead and put that in the surface integral, and basically what we're doing is using equation 8.2, which is Gauss's theorem. I'm using Gauss's theorem to, Gauss's theorem says this, that those two are equal. So what we're doing here, we can convert to index notation to make things a little easier. I don't think you necessarily have to. It doesn't, I don't think it really would matter if you just kept them all as vectors, but I think it's simpler that way. So right here in this next line, that's when we actually implement Gauss's theorem. So we're taking away that normal vector and adding that gradient and taking the divergence of those two vectors there. And from here we can simplify it further by using the product rule and just split those up as so, and that's with respect to dv and v, just like Gauss's theorem says, and that's part A. So for part 2, it's very similar. We have epsilon x stress and a normal vector there, and it's already in index form. So again, we're using equation 8.2 as above. Taking the divergence there of our values, and I noticed this is just going to be a constant, so we can just take it out of the integral, and then again use the product rule, which gives you this. And then I noticed that this is just the Kronecker delta function here, and I put the Kronecker delta function back here in our final answer. Now you could distribute this constant epsilon back in if you wanted to, and you could roll that up with the Kronecker delta here if you wanted to, but I just left it separate, and that's your final answer. Thanks.